Problem 1.50 in Irodov's general physics presents a specific rotational scenario. We are looking at a solid body where the angular acceleration is determined by the specific angle of rotation rather than the elapsed time. Imagine a wheel on a fixed axis. As it rotates, the body experiences a varying force based on its position, causing the rotational speed to change until it decreases and eventually reverses. Standard kinematic formulas typically assume that acceleration is either a constant value or a function of time. Because our acceleration depends on the angle, those basic equations cannot be applied directly. To solve this, we rely on two mathematical steps: applying the chain rule to the definition of acceleration and then performing a trigonometric integration. By utilizing a specific coordinate substitution, we can convert this differential equation into a clear representation of the body's physical motion. We begin with the given equation for angular acceleration, beta. It equals the constant beta naught multiplied by the cosine of the rotation angle, phi. The problem provides our initial conditions. At the starting time, both rotation angle and angular velocity are 0. The difficulty here is the variable mismatch. The acceleration is provided in terms of the angle, but we need to find the velocity, which is usually a time-based derivative. We start with the definition of angular acceleration, the derivative of angular velocity with respect to time. We expand this using the chain rule to express the change in velocity in terms of angle, multiplied by the change in angle over time. That second term, the rate of change of the angle over time, is simply the angular velocity, omega. Substituting that in gives us our primary tool for this problem. Angular acceleration equals omega times the derivative of omega with respect to phi. This substitution removes time from our calculations. We have successfully linked the change in velocity directly to the body's spatial orientation. We place this expression into our original problem statement. Now we have omega d omega over d phi equaling beta naught cosine phi. To prepare for integration, we separate the variables by moving the angular differential to the right side of the equal sign. Now we set the limits of our integration. Using our initial conditions, the lower bounds for both velocity and angle are 0. The upper bounds are the final values of omega and phi. The integral of omega is omega squared over 2. On the right, the integral of cosine results in the sine of phi. We isolate the angular velocity by multiplying by 2 and taking the square root. We include the plus or minus sign to account for all possible directions of motion. This square root introduces a specific mathematical constraint. For the velocity to be a real number, the value inside the root, sine phi, must be 0 or positive. Since sine is only positive between 0 and pi, the body cannot rotate beyond 180 degrees. It hits a physical limit at pi radians. When the angle reaches pi, the velocity drops to 0. At that same point, the acceleration becomes negative, pulling the body back towards its starting position. This confirms the body is oscillating. We can visualize this motion by plotting the angular velocity against the rotation angle. Our calculated boundaries show that velocity is 0 at the start and 0 at pi radians. The maximum speeds occur at exactly 90 degrees, or pi over 2. Here, the velocity reaches its highest positive value on the forward swing and its lowest negative value on the return. Connecting these points creates a closed loop. The upper curve tracks the forward motion, while the lower curve tracks the body as it swings back towards the origin. This closed shape on our plot is the visual evidence of a periodic system. The body is trapped within these specific coordinates, moving in a continuous cycle. We have transitioned from an acceleration defined by position to a complete description of the body's velocity. This derivation shows how the mathematical properties of an equation, like the domain of a square root, define the actual physical behavior of an object. This chain rule substitution is a reliable method for any kinematics problem where the acceleration depends on displacement or angle rather than time. To reinforce this concept, try re-deriving the integration limits on your own. Applying this technique consistently will allow you to solve various complex problems in classical mechanics.